So what we need to do is find the eigenvalues of the matrix, and specifically they're asking us to write the eigenvalues in a particular way. We're going to put the smaller one as lambda 1 and the larger one as lambda 2. So what we want to do is we want to take our matrix 7, 3, negative 2, and 2, and we want to subtract lambda times the identity matrix. So there's a little bit of background theory as to why this is the case. I'm pretty sure it's like A times some vector is equal to lambda times some vector. This is the equation that talks about eigenvalues and eigenvectors. We say lambda is an eigenvalue if this relationship happens, and x is an eigenvector when this relationship happens. Now obviously x is equal to 0, like the 0 vector is always a solution to this for any lambda, which isn't really an exciting solution. So usually we want x to be not 0. And this particular equation comes from the fact that we can, I believe, move the lambda over like so, and we get the 0 vector. So the subtraction of these two things should give us the 0 vector. And then if we right factor the x out, we get a minus lambda I times x is equal to the 0 vector. So we get a homogeneous linear system. And then this here is the new matrix. This is kind of like our new augmented matrix, or kind of coefficient matrix that we're working with. And if we force the determinant of this to be 0, then we actually get the interesting solutions to the homogeneous linear system. So the interesting solutions only happen when the determinant of this is equal to 0. So we're going to find this matrix, A minus lambda I. It looks like this: 7 minus lambda, 3 minus 0, negative 2 minus 0, and 2 minus lambda. And we're going to find the determinant of this matrix and see what happens. So this should give us 7, take away lambda, 2, take lambda, and a subtraction of 3 times negative 2. So let's set this equal to 0, and we should get 14 minus 7 lambda minus 2 lambda plus lambda squared, and then we get a subtraction of negative 6. So it's really like plus 6. So the equation we're looking at is a quadratic equation. Hopefully it's factorable. We have lambda squared minus 9 lambda, and then we should have plus 20. So if we can factor this, that's fantastic. Is this factorable? Can I factor this? Can I find two numbers that multiply the 20 and add to negative 9? 4 and 5? 4 and 5? Minus 4 minus 5? So either lambda equals 4 or lambda equals 5. That should do the trick. One of the eigenvalues of the matrix blah is 5. Find an associated eigenvector. Ooh. Find an associated eigenvector. Chat, can we do this in an easy way? Can we just basically say that A times the eigenvector is equal to lambda times the eigenvector? So we get 21, negative 80, 4, negative 15 times xy is equal to 5 times xy, so 5x and 5y. Is that easy? I don't know if that's easy or not. It doesn't look easy because we'd have to start guessing at values of x and y, right? And I'm not sure it's super obvious what I should pick for x and y. I guess I could try to... It's probably easier to go back to what we had before, which is if I have a minus lambda I times x equals to 0, this is a homogeneous linear system. So our a minus lambda I would look like this. It would look like 21 minus lambda, negative 80, 4, and negative 15 minus lambda. Then we have some kind of 2 by 2 x vector. And then we have the constants, which are both going to be 0 in this case because we've created this homogeneous system. So we could, I guess, put 5 in. We know that lambda is equal to 5. And if we put that in, what do we get? 21 take 5 is 16. And then negative 15 take 5 more would be negative 20. So what we're really trying to think about is how to solve this system. And if we can solve this system, then we should be able to find some eigenvectors for this system. I can see relatively quickly, is 80 divisible by 16? Why does it feel like 80 is divisible by 16? It totally is! So we can take row 1 and divide by 16. I also can see that row 2 is divisible by 4. So that would give me 1, negative 5, 0, and then 1, negative 5, and 0. And then from here we can take row 2, subtract row 1. And just like that, we have a reduced row echelon form for the homogeneous system that we're working with. Let's take a look at what this first equation says. It says that x minus 5y is equal to 0. Or we could say that x is equal to 5y. So we just need one eigenvector, and we know that all of our eigenvectors have to satisfy this particular equation. So any eigenvector, this has to be true.
Grading papers. Zeta boring. I'd rather solve equations.
Now, we do want to make sure that we pick a non-zero eigenvector. So let's take maybe y is equal to 1. So if y is equal to 1, then we have x is equal to 5. So a particular eigenvector could be 5, 1. That should do the trick. So find an associated eigenvector. I don't know exactly how they want these vectors put in, but maybe we'd put it in like this. And of course, eigenvectors are eigenvectors of the system up to some kind of scalar multiple. So as long as we don't multiply this vector by 0, we can multiply it by any other constant, and it still should be an eigenvector of this system. So question 3 says, suppose matrix A is 3 by 3 such that A times this is equal to 2, 3, negative 2, 3, 2. So we have A times, this is our x vector, right? So we have A times x is equal to half x. So an eigenvalue of A must be a half. I can see that the multiplication by A shrinks this vector by a factor of 2, so that must be my eigenvalue. Question 4. I guess we should probably, I'm going to be solving these questions. We should probably remove the music so that I don't get too many copyright strikes. So anyway, just a quick recap of question 3. If I take A and I write multiplied by x, I'm going to be multiplying by a half here. So 1/2 is going to be the eigenvalue that we're looking for. So for question 4, we have a 2 by 2 matrix M. We want to find an eigenvalue. Find an eigenvalue. Wait, does this make sense? Find an eigenvalue, a corresponding eigenvector. What? Find an eigenvalue, a corresponding... Like, that sounds weird. You need only to find one eigenvalue and eigenvector pair. That sounds so weird. Find an eigenvalue, a corresponding eigenvector. What am I, like a dating service? Get out of here. Okay, I guess we should find all of our eigenvalues. We'll pick maybe the easiest one to work with. They're probably all relatively okay. So here's our A minus lambda I matrix. Let's go ahead and find the determinant of this. It should be 1 minus lambda, 4 minus lambda, and then we're going to subtract negative 2. So let's set this equal to 0. This is going to be 4. Take lambda, take 4 lambda plus lambda squared, and then we'll add 2. Okay, is this nice and factorable? 6 and 5 seem like they're nice things, so 3 and 2 are probably going to be nice numbers here. Negative, negative. Minus 3 minus 2, that looks like it will work. So let's pick the eigenvalue of 2. If we pick 2, then we do 1 minus 2, 2, negative 1, and 4 minus 2. This is going to be the homogeneous system that we need to solve. So we have negative 1, 2, negative 1, 2. And we can do row 2 minus row 1. And that should give us our reduced or echelon form. And we'll take a look at that first row, which says that negative x plus 2y is equal to 0. So negative x is equal to negative 2y, or x is equal to twice y. So if I choose, for example, y is equal to 1, so if I scroll back up here and I pick my y component of the eigenvector to be 1, then I know the x component has to be twice that, so 2, 1 would be a possible eigenvector. As long as the x component is twice the size of the y component, we should be okay. So find a matrix A with eigenvalues 1 and negative 2. What? Find a matrix A with eigenvalues 1 and negative 2. Also find the corresponding eigenvectors. That's a fun question. Can we just make it a diagonal matrix? Can we just do 1, negative 2, 0, 0? That seems like a reasonable thing. Okay, so that works, I think. The eigenvalue, eigenvector, vector pairs. So for lambda equals 1, we have 1 minus 1, 1 minus lambda. So I'm looking at this matrix, 1 minus lambda, 0, 0, and then 0, negative 2 minus lambda, 0. So this would be 1 minus 1, which is 0, and then negative 2 take away 1, so we get this. So it's not reduced or echelon form, but I don't need to do too much here. I basically just need to know that negative 3y is equal to 0. So y is equal to 0, and x is a free parameter. So my eigenvectors...
Zeta boring. Try something more Zeta exciting next time.
...are looking something like this. So I need y to be 0 all the time, and x can be anything at once. So I'll just take the number 1. Now, for lambda is equal to negative 2, what do we get? So we get 1 plus 2, which is 3. We'll get 0, 0, and then negative 2 minus negative 2, which is 0. And in this case, we get 3x is equal to 0, so x has to be forced to be 0. And then y is free. Be free, young y. So x has to be 0, y can be anything we want, so I'll just choose y is equal to 1. So question 6, suppose A is a matrix and U is an eigenvector corresponding to lambda equals negative 3. V is an eigenvector corresponding to lambda equals 2. This is an interesting question. So A times the first eigenvector should be lambda times that vector. So here we need lambda times u. or we need negative 3u. So we need to take this vector and multiply it by negative 3. So negative 12. And similar story here. We need this to be 2 times v. So this is the eigenvector-eigenvalue relationship. If I know it's an eigenvector, then I can multiply it by its corresponding eigenvalue to get this equality to work. So this should be minus 2, 4, 2, and 8. Now, what happens if we add these things? Who knows? What's going to happen? What happens if we go a times the sum of the two eigenvectors? That's interesting. What should we get there? Linearity, yeah, so we should be able to add these things up, shouldn't we, Fem? We should be able to go component by component and get our answer. So negative 15 minus 2 would be negative 17, best number. 3 and 4 is 7. Negative 3 plus 2 is negative 1, and then negative 12 plus 8 is negative 4. So yeah, we should be able to go component by component there, and that's because a time this is really just a times u plus a times v. So we know what those vectors look like. They're the two vectors that we've calculated, so we can just add those two vectors together to get our final answer.